Hello students, so in this lecture I will be talking about electrical conductance or resistance associated with adsorption on films. Now if we have a film like this, it can be a metal film. Let's take it as a metal film, and in this metal film we make some impurities to get adsorbed on the surface. So let's call them as impurities. Now these impurities can be again can be a glycol, can be a metaphosphoric acid, it can be tartar, or it can be a citrate. All these adsorption will have an effect on the resistivity rho. Now the decrease in conductance or increase in resistivity, whatever, can be expressed as delta sigma by sigma. This is the decrease in conductance. And it is equal to small x n by n, where small n is the number of molecules adsorbed, whereas capital N is the film or the number of atoms in the film already present. And this is a small number, which is order of 2 for H2O2 and CO. Right. Now we can actually categorize films into two types. We can call it as a thick film, and we can call it as a thin film. How do we differentiate between a thick film and a thin film? We can differentiate by if the film thickness T is greater than the mean free path of the electrons, we call it as a thick film. On the other hand, if it is less than the mean free rate of the electrons, we call it as a thin film. Now, in the case of a thick film, you should observe that the resistivity is generally much higher than its bulk counterpart. Then suppose the film, the material of the film, if present in bulk form, that resistivity will be much lower than in its thin film form. Now the reason for this excessive resistivity is the scattering. electrons at the surface external cavities. And there are many structural defects frozen in during deposition of films, these are structural defects. There can be dislocations, stacking faults, and vacancies. But of which dislocations is the most common, and so we talk about dislocations in films. These dislocations, all you might have known, is the half ton of atoms. So if we have a plane of atom like this, atomic lattice, we have half ton of atoms, and that is called an edge dislocation, and this is your bird's eye vector. So this is most abundant in films, and it is of the order of 10 to the power 10 to 10 to the power 12 dislocation lines per centimeter square. And their contribution to resistivity is very negligible. So negligible contribution to rho, and if the order of 10 to the power minus 19 ohm centimeter per dislocation, so which is very negligible quantity. Now, similar to dislocations, the stacking faults the stacking faults sorry the stacking faults also has very less contribution to the resistivity, and the amount of stacking fault is about 10 to the power 5 per centimeter. This is the usual linear density of stacking faults, and they also contribute very less to resistivity. The large contribution to resistivity actually comes from the vacancies. This atomic vacancies, they contribute a large contribution to resistivity occurs due to these vacancies, and the contribution is order of 1 to 6 micro ohm centimeter per atomic percentage. This is the value. Now this excess resistivity, now we observe that in noble metal films, this excess resistivity is due to vacancy concentration of 0.1 to 1 atomic percentage, and this is actually quite large, than the value at equilibrium. So we need to have some means of achieving this sort of excess atomic percentage of vacancies, and this can be achieved if we do quenching, means rapid cooling. If we rapidly cool the metal, then the diffusion is the atoms don't get any time to diffuse, and the atomic concentration or the vacancy concentration of this range can be achieved. Now, apart from these vacancies, stacking faults, and dislocations, grain boundaries are also a significant source of electron scattering. And again, if the grain size T, here T is not the thickness of the grain size, so let's not take it as T, let's call it as D. If the grain size is much less than the mean free path of the electrons, then what will happen? The diffuse scattering will cause diffuse scattering at the surface will increase, will rise up, and it will add to the resistivity of the film.